The first kind of methods that we'll talk about are embedding learning methods or model-based methods, as we just said. The key intuition of these methods is to address the few-shot learning problem by learning to compare. If a model can determine similarity between two images or the similarity between the semantics of the class labels, which is required for zero-shot learning, one can classify unseen input in comparison or relation to labeled instances seen during training. What's the overall idea? One learns separate embedding functions. Embedding functions are the output representations of a neural network in this context. For training samples, detrain, and test samples, detest. And these comparison models are trained end to end using an approach known as meta-learning, which we'll describe soon. At test time, the prediction is made based on comparing distances between the X test feature and the training set features from each class. So here is the overall schematic. So you have a few-shot training set dtrain and a test sample t-test. You have an embedding for the train set G, an embedding for the test sample F. A similarity is computed to make the final prediction on the class label of interest. What is meta-learning here? Meta-learning is known as learning to learn, and we'll describe that in more detail. If we considered the n-way k-shot setting of few-shot learning, where n of the total number of classes have only k examples, in meta-learning, in each episode, you have a different set of training classes and a set of test examples. And these set of training classes may not be exhaustive and complete the full training data set. These are loosely sampled as some of the classes from your data set. And the goal in this episode is to train a learner which can make a prediction on this test set based on this train set. That would complete one episode of meta-learning in which you get one learner as the output. Now, in the second episode of meta-learning, a different set of classes is again sampled to form your training data set. You have a test set, and once again, the meta-learner refines the learner to be able to solve the problem in this episode. This is repeated over multiple episodes, where in each episode, a different set of training classes may be sampled. And at meta test, you finally have your setting of your training classes and your test samples where you'd like to deploy your final model. The goal here is meta train and demeta test, which are these episodes, have disjoint classes, which means the 5 classes here that you have in meta train may be different from the 5 classes here, but in meta test. But the goal is you have learned to learn a model. So another way of differentiating, in a classical machine learning algorithm setting, you have a training set, you learn a model with certain number of parameters with an objective to get a good performance on a test set. In meta-learning, you have a meta-training set which has its own train and test split, which corresponds to one episode of your meta-learning. You learn a set of meta-parameters theta, which is used to train learners on a new meta-test set. Here is another way of understanding this. You have your training set in each episode of meta-learning. That is used to learn a meta-learner, which teaches a learner to learn a model, and there is a loss induced because of learning across these episodes in each round of meta-learning. If you see here, between the meta train and the meta test settings, the problem setup matches so that once you have trained a meta learner, the meta learner knows how to provide a model for a new set of classes that may come in the training part of the meta test episode. Remember that in meta learning, each episode can have a training and test. So in the meta test, you have a set of training classes. The learned meta learner knows how to produce a model for these set of classes to be able to solve these test samples. Let's see a concrete example of this idea of meta learning. This is known as matching networks, a method that was developed and published in NeurIPS of 2016. And matching networks is premised on bringing together parametric models and non-parametric models. Recall that parametric models learn model parameters from training samples slowly. You ideally require large data sets to avoid overfitting. Unfortunately, in the setting we are talking about, few shot and zero shot, you may not have large data sets. On the other hand, non-parametric models like k-nearest neighbors allow novel examples to be assimilated quickly, and they are robust to a phenomenon called catastrophic forgetting. Catastrophic forgetting refers to a phenomenon where if you have a set of classes for which a model is trained, if you took MNIST and you trained a model on the classes 0 to 6, let's assume that the classes 7 and 8 occur a bit later, and when you train your model or refine your model on the classes 7 and 8, the model forgets what a 0 or a 1 looked like. This is known as catastrophic forgetting, and neural network models are known to be prone to this phenomenon if you don't retrain on the complete dataset, which may not be possible in all settings. Non-parametric models automatically are robust to such a phenomenon. As an example, as I said, could be k-nearest neighbors. So in this method called matching networks, the proposers propose to combine the best of both worlds. So you have a training phase where you learn cosine similarity based embedding models. So you see here that you have a set of samples S and a query sample Q. So S is like your train set in a meta learning episode, and Q is like your test set in that meta learning episode. You learn embedding function F, which gives you corresponding embeddings for the train set and the test set. And then you use cosine distance to measure the similarity. That's what happens in the train phase to learn the Fs. And at test time, once you get these embeddings, a nearest neighbors approach based on the cosine distance is used to classify the test sample. Here is the architecture that was used in matching networks. So you can see here that you have, this is one meta learning episode. You have a set of samples from a given set of training classes. You have a test sample in that meta learning episode. Remember that you repeat these meta learning episodes with a different set of training classes and test sample in each meta learning episode. These training samples are given as a sequential set of inputs to an LSTM, and the LSTM outputs a representation for each of these input training samples, and you also get a representation of the test sample, and then there is a comparison module that looks at the similarity between the test sample and each of these training samples, and that comparison is given in the equation here as A of x hat and xi, where xi's are the different training samples. How do you measure? How do you compute this A function? In this approach, it's a very simple computation. It gets a softmax over the cosine distances between h of x hat and g of xi. So you take a cosine similarity between the test image and each of the training images, and then do a softmax over these cosine similarities to get a distribution over which of these training samples this test sample is closest to, and multiplying that with the class label gives us the final class label prediction for this test sample. One detail here is, if you notice, the LSTM here is a bidirectional LSTM. Why is that so? We don't want this LSTM to actually depend on the sequence of these training samples that are given as input. And by going bidirectional, by doing a forward and a reverse direction in the LSTM, you're trying to counter that dependence on the sequence. An improved idea was called relation networks, which was published in CVPR of 2018. In this approach, the authors question the use of a cosine embedding. Instead, the method proposes to train and learn a data-driven nonlinear metric instead of using the cosine distance metric. This enables the model to extract complex nonlinear relationships among the data samples and thus generalize better to novel classes. And in fact, relation networks are also extensible easily to the more challenging zero-shot setting where you have no samples for the unseen classes. So here is the overall schematic. So if you see here, you still have S and Q, your trained samples and your query sample. They go through a learned embedding, which is given by F sub theta. Theta are the parameters of that network. And now you take the class mean mu for a set of samples belonging to a class, and you compare the query sample to that mean representation of a class. How do you compare? That comparison is also learned by the model instead of using a cosine distance. So in the training phase, you meta-learn both the embedding module, which is F, and the relation module, which is the one that learns the relationship or the distance metric between the representations. And at test phase, given a query sample, you use the relation scores in the embedding space to the mean of each of your training classes to finally predict the class for the query sample. Here is the overall architecture. You have your set of training set in a given meta-learning episode. You have a query sample here that comes in as a separate test sample. All of these go through the same embedding module, F sub phi. You get feature maps corresponding to this xj and all the xi's from S. And now, different from matching networks, relation networks concatenate these feature maps. The yellow bar here corresponds to the features of xj, and each of these other colored bars are features from each of the other xi's in your train set of that meta-learning episode. What happens after you concatenate? This is then fed to a relation module G, whose parameters are again learned, which finally produces a scalar score for the similarity between the xj and each of the xi's, which is given as a vector of relation scores. And finally, by doing a softmax or an argmax over the relation scores, a final one-hot vector can be predicted. How is this network trained? The relation scores Rij are critical for training the network. The loss function is given by argmin over the set of parameters. Rij minus 1 yi is equal to yj. Rather, this says that whenever yi is equal to yj, or the query sample's label matches one of the trained samples label, we want Rij to be 1. Remember, this is squared, so this overall quantity has to be positive. We want Rij to be 1 in that scenario because similarity is high. And whenever the labels don't match, Rij will be forced to go lesser than 1. How is this used for few shot or zero shot learning? In the few shot learning scenario, what we described is exactly what is done. You have an element-wise sum over the embedding module, which gets your class feature map. We combine the class feature map with the query feature map. We just talked about the concatenation, and then we get the relation scores to finally get the predicted label. For zero shot, because you may not have any samples at all for some of your classes, you need what are known as semantic class embeddings. So you get some meta information about a class, could be a set of attributes, could be any other textual description of a class label, or simply take a word-to-vec representation of the class label itself, or any representation, word level representation of the class label itself. Now, the concatenation and the embedding operator compares the embedding of the class label with the embedding of each of those train samples, and that is used to get a similarity and be able to give the final outcome. That's about embedding learning methods. Let's move now to the second kind of methods, database methods, which are hallucination or feature synthesis methods. The intuition with these methods is learning to augment. We saw learning to compare. Now we talk about learning to augment. Here we learn a generative model to hallucinate new novel class data for data augmentation. And by generating more data, we reduce few or the zero shot learning problem to a standard supervised learning problem. How do we do this? A standard approach is to learn a generator that is conditioned on some meta information using the data in the base classes, and then we generate novel class features conditioned on unseen class meta information, and finally we train a classifier on the base class samples and the generated novel class samples. So just to show this, you have your set of training samples in your meta learning episode, a test sample. So using some meta information and using the train samples themselves, you train a generative model, which is then finally given to a classifier to be able to say, of course you have, since it's a generative model, you may have an adversarial component there to decide whether the generated features are real or fake, but you also have a classification component which tells how to classify these final generated features. Let's see a more concrete example. A popular method in this space is FCLS-WGAN. Here the goal is, given a train set of seen classes, we learn a conditional generator G, which receives as input Z, the random standard noise that you give to a GAN, and a class embedding corresponding to each class. Using these, the generator learns to generate image features. We don't need to generate images here because our goal is not really to generate pretty looking images. Our goal is to generate image representations which can be classified, and this makes it a more feasible problem. To ensure that the features generated by this approach are good, there is also a discrimination module which minimizes classification loss over the generated features. So you see here that FCLS-WGAN tries to take some attributes of belonging to different classes which are conditioned on to generate image features. And what kind of image features are generated? These are image features that are outputs of CNN models on standard images. So if you used a VGG or a ResNet as a CNN, you would get a certain representation of the image, and we are now asking the GAN to generate similar vector features instead of generating images. How do you extend this to few-shot learning? So this would be the approach for zero-shot learning, where there are no samples for certain classes, which is why we need the class embedding. However, in few-shot learning, you already have samples from some of the classes, and they can also be used to help with generation. So you may not need the class embeddings for few-shot. You may instead use a generator with just noise itself as the input also when you extend such an approach to few-shot learning. How is such a GAN trained? So this method uses two components, CLS and WGAN, and that's the reason for its name. The WGAN component uses a standard GAN loss, but uses a variant of a GAN known as WGAN or Wasserstein GAN, which is a variant that tries to mitigate the mode collapse issue in GANs. That's the GAN loss that's used here. And there's a classification loss that's used to classify the generated features. So you can see here that you have some images in your dataset. You have a CNN whose output gives you some real features X. On the other hand, you have your generator which takes in a noise vector and some class information and also generates some image features X tilde. A discriminator then takes in X and X tilde and the conditional information class and says whether these X and X tilde are real or fake. But there's also an other loss which takes the generated features and tries to classify them into one of the classes in your class universe. The final loss is a combination of the GAN loss and a classification loss which is weighted suitably using a coefficient beta. So just to repeat, to train the classifier, you use a pre-trained generator to generate samples of novel and unseen classes conditioned on class embeddings, and the classifier is often a softmax classifier that's trained on the train set, which gives you X's, and the generated unseen class image features. So both X and X tilde are together used to train this classifier module in this framework. Hope that gave you an understanding of hallucination or feature synthesis methods. Now let's move to the third category, which are parameter initialization methods, which try to use prior knowledge to alter the search strategy. The key intuition here is learning to fine-tune. We saw learning to compare, we saw learning to augment, and now we talk about addressing few-shot using learning to fine-tune. What does that mean? We learn a set of meta-model parameters which are common to all classes. In this context, we say classes are tasks. Each class is a task. So we learn a set of meta parameters that can be applied to all classes or tasks in such a way that with very few samples for a given class, you can fine-tune those meta model parameters to learn the parameters for that class or task. So here is an overall intuition or method of how this works. For each meta learning episode, you have dtrain and dtest. You update some task specific parameters phi I to minimize the loss of the overall parameters for that class. Remember, you have theta, which is an overall set of model parameters which you initialize your model with. Then you fine tune that to solve only one particular class in your current meta learning episode. Then across all of the tasks in a given meta learning episode, you now update the meta parameter theta to minimize the loss across all of those classes. So you see here, phi I is also here. You can see that phi I is also here in this diagram, which is the model parameter for a specific task. phi3 is the model parameter for another specific task, phi2 is the model parameter for another specific task. We want to learn a theta, which is here, which can easily be fine-tuned to get phi1, phi2 or phi3. Once you learn phi1, phi2, phi3 in a given meta-learning episode, you now update theta as a weighted sum of each of these losses corresponding to each of those tasks. What happens at test time? If you have a few samples from one of those few short classes, you've already learned theta, which are your meta model parameters. You can now fine-tune theta using those few samples to get the model for that particular few short class at test time. Let's see this in more detail. The most popular approach in this category is called MAML, which stands for Model Agnostic Meta-Learning. There have been several improvements of MAML over these years, but we'll talk about the basic method, where the idea is very similar. The task-specific parameters, say phi I, are obtained through optimization. The overall formulation goes like this. Remember, the goal of this category of methods is to learn a prior such that the model can easily adapt to new tasks. Remember, we are talking about this in the context of few shot learning, where we expect a few samples to be there for those few short classes. And by prior, here we mean a good parameter initialization, which is what theta or the meta model parameters try to achieve. So your task specific update is you start by initializing theta, which with any initialization, and in each meta learning episode, you update the task specific parameters, which are theta I prime, which are given by theta minus your loss over theta with respect to the parameters theta and the training set with respect to that particular class I. So that gives you the parameters for that specific class in that meta learning episode. Once this is done, the theta is then updated using theta minus beta gradient, the loss over all of your tasks in that particular episode. In that, of course, now you're getting your images from the test set. Visually, you can look at it as we just explained on the previous slide, you're trying to learn a theta which, if fine-tuned, can easily get you theta 1 star, theta 2 star and theta 3 star, which are the ideal model parameters for class 1, class 2 and class 3. So by meta model parameters, we mean the theta which can be easily fine-tuned. So if you observe the task specific update and the meta update, you would notice that you can now replace theta I prime, which is inside this loss, as theta minus alpha gradient of loss with respect to theta. And when you substitute it that way, you now see that you have theta is equal to theta minus gradient with respect to theta, loss of theta minus another gradient with respect to theta. So in a sense, this becomes equivalent to almost doing second order derivatives on theta. However, this gives an efficient and effective way to be able to compute the updates to theta using this meta-learning approach. Here is an algorithmic view of the same methodology. You randomly initialize theta, you sample a set of tasks in a given meta-learning episode. For the tasks in that meta-learning episode, you sample a set of data points from each of those classes. In that, remember, classes and tasks here mean the same thing. You sample a set of data points from each of those classes in that meta-learning episode. You evaluate the gradient of the loss with respect to each of those classes and update the task specific parameters theta I prime. And then you sample a set of data points from the same classes for the meta update, and then you do the meta update based on these samples by combining the gradients for all of the task specific losses. Remember, Each task is a class here, and that gives you your meta model parameter update that completes one meta learning episode, and then you again repeat and take your next set of tasks, sorry, not here, next set of tasks, and then you repeat this process. We said that MAML was for few shot learning. Can this be used for zero shot learning? A more recent approach shows how this can be done. This is called Meta ZSL, or Meta Learning for Generalized Zero Shot Learning. Here, the idea is to learn a GAN conditioned on class attributes and then train using the same meta learning framework like MAML, and then facilitate the generalization to novel classes. So the key idea here is you use the meta learning framework, where in each episode you have a set of trained classes and test classes, but in each episode we're going to simulate a zero shot learning kind of a setup. Let's see how this is done. So there is a GAN coupled with a classifier module, which leads to three meta learners. You have a generator G, which is a meta learner, learns meta model parameters. You have a discriminator D, which again learns a meta model parameter. And then you have a classifier, which checks the goodness of the generated features. So you can look at this as a combination of feature synthesis methods to do zero shot learning and MAML for the meta learning based approach to achieve this approach. So let the parameters for each of these modules, D, G and C, be theta D, theta G and theta C, and we denote theta GC as the set of parameters combined for theta G and theta C. Now, how is this learning done? You have a given image and attributes for scene classes. You get X and A by passing the image through a CNN. You would get a set of image features X. You have the corresponding attributes A. Then given noise and attributes, you ask the generator to generate features X tilde. Given X tilde and A, the discriminator tries to say whether this is 0 or 1, real or fake. And then you have a classifier which then says whether the generated features belong to a particular class. Right? So this is similar to the feature synthesis framework, but there's a key component here, which is the meta learning framework, which differentiates this and FCLS WGAN. This is done by, the objective now is for the discriminator to maximize the log likelihood of generating X and AC, which are the true image features and the corresponding attributes, and minimize the generated image features and the corresponding attributes. On the other hand, the generator tries to fool the discriminator by taking the attributes and noise and generating an X tilde, and we want the discriminator to call this real, and you have the classification loss. Beyond this objective, you have the meta learning episodes now. The basic updates: now given a meta model parameter theta D, you now get theta D prime for each of your tasks or classes in a meta learning episode, very similar to MAML. And then you perform a meta update at the end of that meta learning episode, which combines the losses for all of the tasks in that meta learning episode and updates theta D, theta GC and so on. So you put the FCLS WGAN in a meta learning framework and you get meta ZSL. Once this is done, the way inference is done is to generate unseen class samples using the learned generator. You get X hats, assuming that you can give the attributes of the unseen class as input to condition the generator. And once the unseen class samples or the features of the unseen class samples are generated, you can use the classifier. You can also train any other classifier to predict the class label for a zero-shot class or any other class in that problem being considered. Hope that gave you an overview of different kinds of methods for few-shot and zero-shot learning, although there are far more. If you'd like to know more and understand more, please go through this excellent tutorial, a blog article on meta-learning, learning to learn fast by Lilian Weng, a nice YouTube video on few-shot learning with meta-learning, a tutorial at ICML 2019 on meta-learning, and a very nice introduction to zero-shot learning.